Hey there, STEM students. This is Miss Rework. This is podcast 9.1, where we're going to learn about acids. So, what are we going to learn about acids? Well, let's review how to name an acid. Okay, remember a binary acid, naming any acids. If it starts with an H, it's an acid. Remember, we have HCl and H2SO4, so HCl would be considered what we call a binary acid, and a binary acid is something that has just a hydrogen and a nonmetal. Right? And then we could also have what we call an oxy acid, which would be if it's hydrogen with a polyatomic ion. Okay, so just a refresher, to name a binary acid depends on the state of the acid. If it's not aqueous, we say it's hydrogen plus whatever the nonmetal is. So such as that HCl gas would be hydrogen chloride. If it's aqueous, however, we have to name it as an acid, so we put hydro, the root of the nonmetal, with ic and acid, so HCl would be hydrochloric acid. All right, and then oxy acids, naming does not depend on the state of the acid. So if it's aqueous, liquid, it doesn't matter. You're going to name it. If it's H something, you're going to name it as an acid. So name the polyatomic ion. You're going to replace ATE with IC, and you're going to replace ITE with OUS. Change the root if necessary for pronunciation, and then add acid to the name. Okay, this is all review, right? Okay, writing the formulas. So when we write the formula for a compound, we're going to identify the anion that's involved. If the acid starts with hydro, then it is a binary acid. It's not polyatomic. If there's hydro, and then if it's hydro, that means it's just going to be hydrogen with whatever else it's attached to. So if it's S, okay, so H and S, or H and N, right? And then the charge for that becomes your subscript. It tells you how many hydrogens you need to have. If there's no hydro at the beginning of the name and the acid ends in IC, then the polyatomic ion must end in ATE. Remember, I ate something icky. If there's no hydro and the acid ends in OUS, that means that the polyatomic ion must end in ITE. Okay? If there's a prefix on the name of the acid, then there's a prefix on the name of the polyatomic ion, and it has to say, such as hypochlorous. Hypochlorous comes from hypochlorite. Okay, so make sure that that prefix stays. And then we use the charge of the anion to decide how many hydrogens we need to have in the formula. All right, so here's some examples. We'll only go through a couple of them to make sure that you have it, and then we're going to move on. So carbonic acid, there's no hydro, so we change the IC to ATE, which makes it carbonate, CO3 with a -2. Okay, hydrogen has to go at the beginning. The 2 becomes your subscript, so it's going to be H2CO3. Good, right? Okay, what about nitrous acid? Okay, IOUS becomes ITE. Nitrite is NO2 with a -1 charge. Has to have hydrogen at the beginning. That becomes your subscript, so HNO2. Now let's try another one. How about hydrosulfuric? Hydro means that it's just binary. It's hydrogen and something else. Sulfuric is sulfur, so sulfur with a -2 charge. The 2 becomes your subscript, so H2S. All right, like I said, just review, so you should be able to do the rest of them on your own. Okay, so let's talk about types of acids. So we have what we call an Arrhenius acid. And in an Arrhenius acid, the acid will produce hydrogen ions in an aqueous solution. Okay, so bases are going to produce hydroxide ions when they're dissolved in water. And the problem with this is that it limits it just to aqueous solutions. So it's saying that you can't have anything as an acid and a base if it's not in an aqueous solution. Okay, and then the other problem is that there's only one type of base that's accounted for, which are those with hydroxide ions in them, and that's not good. Okay, so in this case, we couldn't have sodium hydrogen carbonate or sodium bicarbonate, which is baking soda. And we know that baking soda is something that we use to neutralize those acids if we spill them in class, so that would not be a base, considered according to the Arrhenius definition. And well, we know it is, right? So we've got another definition that we use. It's called the Bronsted-Lowry definition. Okay, according to the Bronsted-Lowry definition, an acid is a proton donor, and a base is a proton acceptor. Okay, so what does that mean? That means that an acid is one that can give a proton away or a hydrogen ion, and a base is a substance that can accept or take on that hydrogen ion. Right? And in a Bronsted-Lowry, acids and bases will always come in pairs because you have to have one that accepts and one that donates. Well, if one's donating, where's it going to go? It's going to go to the one that's accepting. Okay, hydrochloric acid is an acid. Why? Because it can give away. Hydrochloric acid can break down into hydrogen ions and chlorine ions. Look, it's giving away hydrogen ions. Okay, when it dissolves in water, it gives its proton to water. So what does that mean? Well, that means that you have your water and it can take on that hydrogen ion and it can become what we call hydronium ion. Hydronium ion. Okay, and that's just another way that you can look at hydrogen ions. Water is considered a base because it makes that hydrogen ion. It can take that, it can accept that ion. Okay. A neutralization reaction, remember this is an acid-base reaction. In an acid-base reaction, you're going to have water and a salt would be the other product, an ionic compound. The salt's name and formula is based off of the cation of the base and the anion of the acid. Okay, so an example of that would be, let's say we have neutralization reaction. Let's do NaCl. Nope, sorry. Okay, we need a base, NaOH, and we need an acid, HCl. Right, we're always going to form water, and then the salt would be from the cation of the base and the anion of the acid, so NaCl. All right. A neutralization reaction is one way that we use to produce pure salts. Right, and then amphoteric substance. Amphoteric substance is something that can act as either an acid or a base. So water is an amphoteric substance. It has a pH of 7. It can act as an acid if it's mixed with a base, and it can act as a base if it's mixed with an acid just because of the pH differences. Okay, you will eventually get to something called titration. You have a lab where you'll do a titration lab. Okay, and in a titration lab, it's just a method used to perform a neutralization, and it's used to determine the concentration of an unknown acid or base. Okay, so what you're going to do here is you have your ring stand. Let's see if I can change my color real quick so you guys can see this. Okay, so here's your ring stand. Right? I can't draw very well, but that's okay. Okay, your ring stand is here. This right here would be a clamp. It's called a burette. That was cute. A burette clamp, and it holds the burette, which is this glass object here. It holds it still, and the burette, it's graduated, so it has lines on it that you can read the volume. Right? And then this right here, it says tap. That's called the stopcock, and you would turn it to allow the liquid that's inside the burette to come out into your flask. Okay, now we call that substance, that liquid that's inside your flask, is called your titrant. Okay, and that's what's being used to titrate the substance that's inside of your flask. And then as you're allowing that liquid to come into your flask, you allow it to go slowly, and I'll do an example of this in class for you today. But you'll allow that liquid to come into the flask slowly, because inside of that you'll have something called an indicator. And the indicator is something that's one color in acid, it's another color in base, and it's actually, some of them will have a third color if it's in the pH range of the equivalence point. Okay? And what is the equivalence point? Well, the equivalence point is what we say is the part where your equivalence. Okay, the equivalence point is when your concentration of hydroxide or of hydrogen ions, that bracket around it stands for concentration. Your concentration of hydrogen ions is equal to your concentration of hydroxide ions. Okay. And then when that color change does happen, we say that you're at the end point of the reaction, and that's where the indicator will change colors for you to show you. And it depends on what indicator you use, depends on what color change you get. Okay. While you're doing this, you're allowing that titrant to drip into your flask very slowly, because if you don't do it slowly, you will pass your equivalence point and go way past your end point, and then you'll mess up your stuff and you have to do it all over again. Right? And while you're doing this, you're going to be mixing the contents of the flask so that they will stay nice and mixed and they won't be all clumped up and then mess up your results. Okay? And again, I'll show you what this looks like in class. Okay. Last thing we need to talk about is conjugate acid-base pair. Okay, so the conjugate base is what's left after an acid gives up a proton or a hydrogen ion. Okay, the stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger the conjugate base. So an example of this here is sulfuric acid. Sulfuric acid can give away one hydrogen. Okay, so it's going to give away a hydrogen and you're going to be left with HSO4. So H2SO4 is your acid. Your conjugate base for this would be the HSO4. Okay, let's say we have, let's just do H2O. If H2O takes on a hydrogen ion, it becomes H3O with a positive charge, right? So this would be now considered your base. This would be your conjugate acid. Okay, and so that's all it means, is that the conjugate base is when the acid gives away a hydrogen ion. The conjugate acid is when the base takes on a hydrogen ion. And that's all it is, right? Okay, so if it's a stronger acid, it's a weaker conjugate base. If it's a stronger base, it's a weaker conjugate acid, right? Okay, and I think that's it, guys. Yeah, that is it. All right, so hopefully that'll get you started on this whole conjugate acid-base pair thing, and I'll see you in class.